And with that, I think I will move on now to the second session, and I will also get back to that first question we had. So why Singularity on HPC? So Docker was the first container engine, and it is great. It's great for IT. It has got quite interesting features that make it even more powerful for some aspects compared to Singularity. But Docker has also some shortcomings that make it basically unusable on HPC. The major one is possibly the requirement to run Docker with sudo. So every Docker command that a user would issue on the shell would need sudo privileges, even for downloading an image or running an image. And this aspect alone makes it unusable on HPC, because administrators just can't let users of a shared facility to have sudo rights. So that's one of the main reasons. Singularity needs to be installed by administrators with sudo privileges, and parts of its runtime also need some sort of root privileges. But the key difference is that users do not need sudo privileges themselves to be able to run it. So that's kind of a security reason, if we want. As there was the question, let me just briefly mention that there is still a possible component of security issue, in that, as I said, some functions in Singularity are basically run by root. So what we are doing there is basically we're relying on the fact that programmers and developers of Singularity are doing the right things when you write the source code, and they are not leaving bugs in the code that might allow privilege escalation. So I'd say there is a potential concern there. What I can say is that up right now, there hasn't been any report of critical security breaches due to using Singularity and being able to escalate to root. It's definitely something to keep an eye on. Right now, it's not been a big real concern in practice. There are other good reasons for using Singularity on HPC. So Docker comes from IT, so IT folks wanted a tool that comes with isolation by default, and that's great to enforce a number of practices in IT. But in HPC and scientific computing, we are in a different context. We want the users possibly to have the more seamless user experience that they can have. And Singularity comes handy in this regard because it comes with integration with host by default, which means that by default, when you run a Singularity container, we are running with the same user name and user privileges than the host user. You are running in the same directory, and you're seeing the same files as the directory you're running it from. You are, by default, sharing the same shell variables than the host, and you're also sharing the same network and communication port. This aspect basically translates in the user in the fact that the syntax that the users need to learn for using Singularity is much simpler compared to Docker, and that's because developers of Singularity did the work in making this default as friendly as possible, considering a scientific computing audience. And then also Singularity comes with a native compatibility with a number of interesting tools, such as job schedulers like SDERM and PBS for HPC sites, MPI for parallel applications, GPUs for GPU-enabled applications. So if you need to run or interface to this type of technologies, the amount of work you need to do as a user with Singularity is really limited, if not zero. The only drawback in using Singularity, or the main one, is about building images. Because of the way Singularity is designed, to build an image yourself, you will still need root privileges. So you need to run the build with sudo, which means right now you can't really build the Singularity image right from an HPC center. And so the workflow we suggest is actually to build images either on your laptop or workstation or on a cloud service, and then ship your image to HPC for runtime and production. And this is possibly, again, on the user side, the main drawback right now. I've already mentioned some useful container registries that you might be using to download pre-made images for your work. So I won't spend much here. And so let's now move to the first bit of a hands-on demo for today. We're going to cover the very basic commands of Singularity when using containers. So commands to execute shell commands inside a container, commands to enter into an interactive terminal shell inside a container, and then commands to download and store container images. So I now switch screen and move to a shell in my terminal. So today I'm gonna connect to a virtual machine on the Pawsey cloud, on the Nimbus cloud, where I've prepared the material for this tutorial. So let me just do some housekeeping. This variable might be handy later on. You don't need to care about that. So I start and just change directory to a place where I'm running this first toy commands. So first thing we're gonna use for this very first example, kind of a silly container image. It's a Ubuntu image, so nothing really fancy. It's not a powerful scientific application. It's just a basic image that ships with a basic operating system. And I'm doing that because it's small to download, so it will be kind of a fast process, which will allow you to just see the basic commands of Singularity in action. So what I'm doing here, I'm using the Singularity main command, Singularity, followed by exec, which is the Singularity syntax to execute commands. This is a Ubuntu image I'm grabbing from the library. And when library here is the Singularity library, the first one I showed you earlier on my web browser. And then as a command, let me just visualize with cat the content of a file that is present on any Linux box, which basically just tells you the version of the operating system you're using. So when you run this command, you see if the image is not available on your computer already, it will download it from the library image. See here. And once that's done, you will get the output from the command. And here is the output of this cat etc os release. And you can see that I'm running Ubuntu 16.04, which matches actually the version of the container I was using. And this is also nice because I can run the exact same command on the host machine I'm using today, on the Pawsey Nimbus machine. And here you see it's a different, it's still Ubuntu, but it's a different version. It's 18.04. And this is just to give you a kind of first idea that I'm actually running two different operating systems. We have 18.04 on the host machine, but when I run instead inside a container, I'm getting something different. And because I'm actually running an isolated environment, the container environment. So let's try some other execution commands. So you can basically really run any Linux command you would run on a Linux box, and it would just execute inside the container. An interesting thing to mention is that the Singularity library, as I told you before, is not very popular. There are really just a few images in there. So the one that we will be using more often will be Docker Hub. And so you can download and use container images from Docker Hub with Singularity by prepending the Docker prefix. And you will see here again, there will be a process of downloading the image. This is quite important and interesting. So one thing to know is that Docker and Singularity use different agreed formats to pack and embed an isolated environment into containers, which means that, for instance, Docker is not able to run Singularity images because of this difference. On the other hand, Singularity is able to run both Singularity and Docker images, which is great. It means that it doesn't matter how you pack and ship your images, Singularity will always be able to run them. So it's quite compatible as regards the runtime. So that's why you got much more output in the process of downloading the container. That's because Singularity had to convert the Docker image from Docker Hub into its own format. And so here is a lot of output. The very last bit is creating CIF file. And here CIF just means Singularity image format. So what Singularity has done here was just to convert the Docker image into a usable form for Singularity. And then after that comes the command that I asked to execute. Of course, now it took a lot of time because Singularity had to download and convert the image. If I repeat the command again, it will be much faster. And that's because Singularity is able to cache the images that you use in the local disk. And so when you reuse them, the execution time will be much faster. All right, let's mention something more about this image syntax and naming conventions. So the first thing that we have here is the online registry we're using, so Docker in this case. Then we have a container image name, and then we have this string after the colon, which is called tag, which is normally used to specify the version of the software inside the container. One is actually also able to not specify the image at all, in which case the container runtime, Singularity in this case, will default to the last version, to the latest version of container that it can find on the online registry for that application, Ubuntu in this case. And we can get a proof of that if we use again our command to print the version of the container. And you'll see now something different compared to previous examples. You see it's still Ubuntu, as you might infer from the name of the image, but now the version is 2004. It didn't take much time to run because I had used this machine before and the image was already pre-cached before this tutorial today. But the key aspect is that if you don't specify the tag, you just get whatever latest version is available in the registry. And there is an important point here. So you might think, well, that's handy. It can save you some typing. And you also grab always the latest and greatest version of any package. Well, in the end, we end up discouraging this type of practice when using containers, because what happens is that you might lose in the reproducibility of your workflow, because basically the latest image in a container registry is something that can change over time. It's not under your control. It's the people that maintain the registry that might decide one day that, say, Ubuntu 22 comes out and then the latest image becomes Ubuntu 22 and you don't realize that. And the software stack of your analysis changes and your reproducibility is kind of compromised. So this is a possibility, but it's good to stay away from that, basically. So it's always good to specify the version, whichever it is, for the container you want to use. Then there is a couple of more commands I want to show you before moving on. So Singularity has a command, which is Singularity shell, that allows you not to execute an application or command inside the container, but instead just to open up an interactive shell inside the container. So basically, when you run Singularity shell, you are able to create the container and move with the shell inside it for whichever use. This can be useful, for instance, when you have just downloaded an image, if you need to inspect its content, if you need to get to know which type of programs and executables you can execute there. And we're going to use this command later also to inspect the actual content of the file system of the container. Once you're done, you can just exit the shell as you would do with a normal Linux shell, and this would close the container, stop the process, and move you back to the host machine. So one last command to show you is Singularity pull. So as I said before, when you execute commands, Singularity will cache the container image somewhere in your local disk. But maybe in some software setups, you might instead prefer to organize the containers yourself inside the directories, maybe creating a directory tree which is organized by type of applications. So Singularity Pool allows you to make a copy of the container image in a directory of your choice, which by default is just the current directory. And in fact, you can see here that after the Singularity Pool command, this file has appeared, ubuntu_1804.zip, which is just a copy of the container image we downloaded before. And so, for instance, now rather than keeping on using the full name specification for the container image, I can just run the container by using this file that I have downloaded. And that can be just a useful alternative to be aware of. Just one last word on the syntax, on the naming convention for a container on online registries. We used in these examples Ubuntu 1804. So basically, let's stick, for instance, with the Docker syntax. Here, Ubuntu was the name, 1804 was the tag or version tag, and we were with the Docker prefix. We could omit that because Ubuntu is a part of the general library in Docker Hub, but very often you would have one extra string in the container name specification, which basically represents the repository or say the name of the developers that developed the container. So it might be, I don't know, Rocker for R and R Studio images. We'll see that tomorrow. It might even be the name of a lab that has uploaded containers on Docker. Might be Pawsey. There is a Pawsey SC repository in Docker. If you use key.io bio containers, you will need also to add key.io in the name specification of the container. You don't have to worry too much about that because when you look for container images on the website, on the web browser, on your registry, you will get prompted about the full syntax to use it. This is just for you to be aware of these different syntaxes. And that's it. I think now I'm happy to take a couple of questions from the audience.
Okay, so there's a lot of discussion going on. Great discussion. Just going back to container versus image, if you could just make that distinction again.
Yeah,
that would be good.
Yeah, so think at first this is kind of a bit confusing. In the end, we end up using the two words in an interchangeable way. It doesn't really mean much when you actually use them. It is mostly like for appropriate understanding and abstraction of the concepts. So think about a normal application you would download or install on your computer. You would have a directory somewhere in your computer which contains all of the files for your application. But then when you actually open the application, you would have a running process that runs on your computer that allows you, say in the case of Word, to open up a text editor and use it. So you have this distinction with normal applications between the files that you need to run the application and the actual process, the instantiation of the application. And so images and containers match these two concepts. So images are the collection of files that you need to carry over to your machine to actually use the containerized application. And the container is the running instantiation of that image. So it's the actual running process that you spawn, that you start up to use the application. And that's about it. In the end, it doesn't really matter if you mix the two terms. It's just that they are two distinct concepts.
Okay, thanks. One more. Marco, you mentioned scalability. I imagine Singularity containers need to be spun up for every task that I wish to run in a parallel. What is the compute overhead like for spinning up the container for every single parallel task?
Quite small, actually. So Singularity was optimized for that because it was designed for HPC. So we're going to see an example on the third webinar this week on Wednesday. The overhead is really minimal. So Singularity is able to interface natively with no extra care, basically, with the resource manager on your HPC site. And basically will behave as any other application. So you will have a resource manager that spawns not one, but multiple instantiations of a Singularity container. And that's it, basically. The overhead is really limited. One thing that personally took me just some time to realize is that even if a container can be, say, 1 gigabyte in size, because it has a lot of files, when you actually run it, you don't have to load all of those files in your memory, because it's really like just an embedded and isolated file system. You only pick and load the files that you need to run the functions and commands you need for your particular user case. So it's you don't have any overhead because of the fact the container is big, and same, you don't get any overhead because you're spawning multiple instances. It basically, as I said, behaves as any other application, which is spawned through a resource manager.